Our model explains nicely how the moon's motion once about a synodic month to the east relative to the sun controls moonrise and moonset times, as well as the appearance of the moon in the sky, the phases. You may have noticed that when I was demonstrating new moon and full moon, I had to cheat a little bit. I had to move the moon vertically, up and down, to make the appearance of the full moon work out, for example, the way we wanted it to work out. Does the moon move up and down? Well, if in our model the motion horizontally to the left represents the moon's motion to the east, up and down motion represents motion north and south along the celestial sphere. And the question we're trying to get at is, what is the moon's declination? So what is the moon's declination? Well, remember that the sun's declination changes periodically over the course of the year. The sun does not move along the celestial equator. It moves along a tilted circle, tilted 23.5 degrees relative to the celestial equator. We call that circle the ecliptic. Now, for example, when the moon is new, the moon's right ascension is the same as that of the sun. This means that the sun and the moon rise at about the same time. If the moon's declination at that time were exactly the same as the declination of the sun and the moon would be in exactly the same point in the sky, and we would not be able to see both. We'd be able to see probably only the moon since it's closer, and the sun would be invisible. It would be hidden beyond the moon. Of course, this does not happen every new moon. The reason it doesn't happen every new moon is because the moon's orbit is about the Earth is not in the plane of the ecliptic. The moon does not orbit the Earth exactly along the ecliptic. If you were a space monster observing the Earth orbiting the sun, and as the moon orbits the Earth, you'd notice that the two orbits are almost exactly coplanar, but there's a tilt, and the tilt of the moon's orbit relative to the ecliptic is 5 degrees. 5 degrees doesn't sound like much compared to, say, the 23.5 degree tilt of the ecliptic relative to the celestial equator. But remember that the moon and the sun are about the same size in the sky, and the angular diameter of each of them is about half a degree. This means that when the moon and the sun occupy the same right ascension, if their declinations differ by, say, 2 degrees, that's still 4 times the size of either sun or moon in the sky, and they certainly do not occupy the same point in the sky. We can see both the sun and the moon, although we only see the sun because the sun is much brighter. But the moon certainly does not obscure the sun if it is 2 degrees north or 2 degrees south of the sun. In order for the moon to obscure the sun, they have to be at the same right ascension and at the same declination. Is that possible? Well, yes, of course it is. Remember, what I said is that the moon's orbit is tilted by 5 degrees relative to the ecliptic. Just as the ecliptic being tilted relative to the equator means that there are 2 diametrically opposed points that are common, at which these 2 circles are sort of hinged. Those were the equinoxes. When I have the moon's orbit tilted 5 degrees relative to the ecliptic, there are 2 diametrically opposed points at which these 2 circles intersect. Those are called the nodes. What are these nodes? These are 2 diametrically opposed points that are both points on the moon's orbit around the Earth and points on the sun's orbit around the Earth on the ecliptic. This means that if the moon is at one of the nodes and the sun is at the node, remember the node is a point both on the ecliptic and on the moon's orbit, both objects can be at the same point. And if they happen to do that at the same time, then the moon can and will obscure the sun, and interesting things will happen. Let's see in a demonstration how exactly this works. In our first lunation, I carefully kept the moon way north, or up in this image, from the sun when it was full, and way south of the sun when it was new. What we're going to do now is see what happens to the full moon when the line of nodes is aligned with the direction to the sun. In other words, the moon, when it is 12 hours away in right ascension from the sun, is at exactly the sun's declination. And we start our demonstration with the waxing gibbous moon, and it waxes until it is becoming full, and then what we see is that from the eastern side of the moon, a fuzzy shadow covers the surface of the moon. Of course, this is the shadow of my head. It would not be as shaggy were it the real Earth, but this is exactly the geometry for a total lunar eclipse. The moon enters the shadow from the west moving east, and therefore it moves out of the shadow, starting with its eastern edge first. So when you see a lunar eclipse take place and then the moon uncover, you're literally watching the moon orbit around the Earth. About 2 weeks later, or 2 weeks earlier, the moon is now at the sun's right ascension. We're getting a new moon, and the moon is still at the same declination as the sun, and we'll see what happens. We pick up the story with a waning crescent moon. The moon moves in front of the sun. When it is at the sun's right ascension and declination, the the moon in fact is obscuring the sun. And remember, we're on the daytime side of the Earth. This is midday because it's a new moon. We shouldn't be able to see it at all. In fact, we don't. But then we don't see the sun either. We get complete darkness in the middle of the day. And as the moon continues to move to the east, we see this weird glow on the moon. This is an artifact of a shiny GoPro camera, but even this is instructive. The lens of the camera is still eclipsed, but the bits of the camera on the right-hand side are already shining in the light, and there you can see the reflection of that off the moon. This is what would happen if people living a few thousand kilometers to the west of you erected a huge shiny tower on Earth during a total solar eclipse. You might see the reflections from that shiny tower on the surface of the moon, and then as the moon continues to move east, the sun is again revealed and it's bright midday. What did the model show us? The model showed us that we can get an eclipse, a lunar eclipse at full moon or a solar eclipse at new moon, if the moon is full or new at the same time that it is on one of the two nodes on the points where the moon's orbit intersects the ecliptic, hence the name ecliptic. If the moon is on the ecliptic and new or full, then we can get an eclipse. Now, what does this mean? Well, for the moon to be new or full means it is either at the same right ascension of the sun or 12 hours away, diametrically opposed to the position of the sun. If the moon is on a node and either at the same right ascension or opposite right ascension to the sun, this means the sun itself is at one of those two nodes. This gives us twice during an average year something called an eclipse season. And the alignment need not be absolutely perfect because neither the sun nor the moon are point-like objects, but there are two sort of 1.5 month periods during each year, and in those 1.5 month period, eclipses may occur. May occur, that is, when the moon is either full or new, so that it is at the correct part of its orbit, at the right ascension, either of the sun or opposite that of the sun, and now at the right declination. So twice a year we have an eclipse season, and during an eclipse season you have usually between 2 or 3 eclipses, one of one kind, and flanking it 2 weeks on either side, 2 of the other kind. So you could have a solar eclipse flanked by 2 lunar eclipses, or a lunar eclipse flanked by 2 solar eclipses. By the time the next eclipse of either type would have occurred, the next new moon, for example, the sun is now too far from the line of nodes, and you no longer get an eclipse. So typically no more than 3 per season. And this should happen twice per year. In fact, like everything else that is tilted, the line of nodes wobbles. In other words, the tilt between the moon's orbit and the ecliptic is always 5 degrees, but its orientation wobbles, and as is the case with the Earth, it actually wobbles to the west because it is orbiting to the east. And so the tilt precesses to the west very slowly, once every 18.6 years or so. And this just means that the eclipse year, the year during which 2 eclipse seasons happen, is a little bit shorter than the full orbital year of the Earth, only 346.6 days. And so during each of those 2 eclipse seasons, a new or full moon might lead to a solar or lunar eclipse. A new moon during eclipse season means the moon is in front of the sun and at the right declination, so you can have a solar eclipse. A full moon means the Earth is between the moon and the sun, and the Earth's shadow will obscure the moon, just as my shaggy head obscured the moon in our model. Now, we need to get a handle on the relative sizes and distances of things to understand the difference of the 2 phenomena. So, the moon and the sun are almost precisely the same size in angular terms in the sky. If you think about it, the sun is much larger than the moon. From our small angle approximation, we know that it is much farther. The ratio of their sizes is almost precisely the ratio of their distances, so that both the moon and the sun appear in the sky to be about the same size. An interesting coincidence. What this allows is when you have perfect alignment during new moon, the moon is able to completely obscure the sun when you superpose 2 disks of the exact same size in the sky. But this requires perfect alignment, so perfect that in fact it will only obtain for a small region on Earth if you move a little bit away from that region on Earth, then the alignment is no longer perfect. The alignment is only perfect at one point on Earth. And when I say one point, I mean a region on Earth whose size is up to about 250 kilometers. That's a very small part of a planet with a radius of 6,400 kilometers. And in that region where the moon's shadow completely obscures the sun, you get what is called a total eclipse. And we have here a beautiful time series of a total eclipse. Notice that as time progresses in this, the moon seems to obscure the sun from the left, whereas in my, and then leave the sun to the right, whereas in my model this was happening the other way around. The reason is that this eclipse in 2001 was observed near Zimbabwe, and near Zimbabwe you're in the southern hemisphere, which means east and west are still the same, but looking, since the sun is now to your north, the moon entering the sun from the west, moving to the east, is now from the left to the right. So a nod to our southern hemisphere viewers. This time it makes sense to you. The moon is coming from the west to the east across the surface of the sun. It obscures the sun completely for a few minutes and then is seen to move away. And what we're watching again is the moon orbiting the Earth, although also this place, Zimbabwe, is being moved along the surface of the Earth by the Earth's west to east rotation and moves out of the shadow, as we'll see in a moment. And noteworthy, when the moon completely obscures the sun, a region around the sun that appeared completely dark before is suddenly seen to be brilliantly luminous. This is called the corona, the crown of the sun. It is not visible when we see the sun itself, or the sun's disk, because the sun's disk is so bright that it blinds us to the brilliance of the corona. But once you obscure the sun's disk, you can see that the region around the sun's disk is illuminated. When we talk about the sun, we'll try to understand what this glowing crown is and how to observe it away from eclipses. A more common phenomenon than this beautiful totality is that when the new moon occurs, the line of nodes is not exactly aligned with the sun, and so the moon is a little bit south or a little bit north of the sun, and then the moon would have passed below or above the sun, above it if it were south, since we're in the southern hemisphere, and below if north, or the other way in the northern hemisphere. And then you will find a partial eclipse where not the full surface of the sun is obscured, but only some fraction thereof. And this is far more common because it requires a less sensitive alignment. To give you a sense of what the shadow of the moon on the Earth looks like, here's a beautiful image taken from the Mir spacecraft on August 11th, 1999. And this is an image of Earth, and what we're seeing on Earth is the moon's shadow. So the moon's shadow, as I said, obscures the moon can obscure the entire sun in this inner circle of radius about 250 kilometers. Away, we see this partial shadow. These are regions where if you look up, you can see part of the sun, but some fraction of the sun is obscured by the moon. You can see around it a little bit, and so this is called the penumbra, or partial shadow. People here see a total eclipse. People here see a partial eclipse. And now remember that underneath this shadow, the Earth is rotating, so that this shadow is effectively moving along the Earth at some 1,000 kilometers per hour, and so each individual location only gets a short period of totality. Now, this is what happens if alignment is perfect and if the moon and the sun are indeed exactly the same size in the sky. How can they change? Does the moon shrink? No, but the moon's orbit around the Earth is not completely circular. The moon is sometimes a little closer to Earth and sometimes a little farther. When complete alignment occurs and the moon is on the farther part of its orbit, it's just a bit farther from Earth. Since its size didn't change, its apparent size in the sky is a little bit smaller. It's then smaller than the sun in the sky, and we get what is called an annular eclipse, because you see an annulus of sun, a ring of sun surrounding the moon. This shadow here is the moon. We see some of the corona and even some of the chromosphere around the sun, But what we also see here is a little bit of the disk of the sun, the photosphere as it's called, and the moon not completely obscuring it in this beautiful image of an annular solar eclipse. This is what happens when alignment during eclipse season occurs at new moon. During full moon, what happens is that the Earth's shadow prevents sunlight from hitting the moon, and the moon becomes dark. The moon, as I said, is moving to the east. It enters Earth's shadow from the west. Again, the eclipse can be total or partial, and depending on the quality of the alignment. And we can get a penumbral eclipse when the moon is only in partial shadow. In other words, where from the moon you can see some part of the sun, but some of the sunlight is blocked by the Earth, just as pieces of the Earth were in partial moon shadow. Then the moon just slightly dims. It's kind of hard to even notice it. But when you get a total eclipse, when some part of the moon's surface is completely obscured from the sun, then this is the beautiful image you see. Now this image should surprise you. I mean, perhaps some sunlight is reaching over here. Maybe I didn't time this photo to precise totality. But where is the light coming from that allows us to see the moon, this side of the moon at all? This side of the moon is in fact in total Earth shadow. You cannot see the sun from this area of the moon. The Earth is bigger than the moon, so it handily obscures the sun. It's much easier to arrange a total lunar eclipse than a total solar eclipse. And also, a lunar eclipse, when it occurs, is visible, since the moon is dark, to anybody on Earth who can see the moon. So whenever it occurs during your nighttime, you can see the moon eclipsed. It's a far less delicate arrangement than the solar eclipse, which only blocks out the sun for a small fraction of the Earth. As indicated on the slide, the light that is reaching the moon, despite the sun being obscured by the Earth, has passed through the Earth's atmosphere. It has in fact been refracted, so deflected a bit by the Earth's atmosphere. Why passing through the Earth's atmosphere makes the light red, or causing this beautiful and famous wine red coloring of the moon during a total eclipse, is something we'll discuss in a week or two. This is a picture actually taken at our observatory in the solstice eclipse of December 2010. And so this is a pretty image, and lunar eclipses are easier to find and observe. I encourage you to enjoy them. A few more fun facts about the moon while we're discussing the moon. So, two well-known things that people appear to observe. One is that when you see the moon rising or setting, it's near the horizon, it appears larger. This, it turns out, is a psychological illusion. Taking pictures of the moon with a camera, you can measure its angular size. And in fact, if anything, then strange optical effects make it appear a little bit smaller in the sky near the horizon. But there are various psychological theories near the comparison to other objects nearby, angular corrections. I'm not an expert on the psychology, but it does appear to us that the rising full moon seems huge when it's on the horizon and small when it's high in the sky, but this is completely in our heads. On the other hand, there's this other famous illusion which is called seeing the old moon in the new moon's arms, which is that when you see a crescent moon where only a fraction of the moon is illuminated, then you can sometimes imagine to yourself that your mind completes the full disk of the moon, and you can see the part of the moon that is not illuminated by sunlight. And this one is a physical effect. Here's a camera capturing it. Here's the illuminated side of the moon, so the sun is down that way. This side of the moon is dark, sunlight cannot reach it, and yet I see it. So there's some light hitting it, and the reason, of course, is that when the moon is a crescent, if you were on the moon, set up the configuration in your head, you would see that there would be a full Earth in the sky, and viewing the full Earth in the lunar sky means that there is bright Earth light illuminating the moon. So the light that is hitting the moon, by which we are seeing this moon, is Earth light. In other words, light that was emitted by the sun, reflected by the Earth, hit the moon, reflected off the moon, and came into the aperture of this camera. So the fact that you can see the dark part of the moon when the moon is a crescent is not psychological, it is true. You can only see this when the moon is a crescent, basically because once the moon becomes too bright, it blinds us, it dazzles us, and we can't see this. Also, the larger the illuminated part of the moon, the less of the face of the earth is illuminated. Of course, when we have a full moon, then people on the moon would see a new earth. The phases are complementary. And so, for both of those reasons, we only see this when the moon is a crescent.